Hello, everyone. Today we're going to continue with combinatorics. So this is assignment 1, year 11. And I'm going to share my screen. And yes, lovely. So the first question is, a fair coin is tossed 6 times. Uh, how many sequences contain exactly 3 heads? Well, we can, how many sequences contain, so out of we want to know how many there are possible sequences there overall, and the number of possible sequences is so a number of possible sequences. Well, if you think about it, you can draw a tree diagram. Yeah, so it goes heads or tails. The second row is heads or tails, and heads, tails, etc., etc. Um, yes, my room. You can always access Miro through the website, through our COMPOS website. You can see that at each stage you have 2 possibilities, and because there are 6 coins, and there are 2 possibilities for each, there's going to be 2 to the power 6, which is 64 sequences of heads, heads and tails. Lovely. So that's the overall. But how many contain exactly 3 heads? Well, if it contains exactly 3 heads, we know that it has to contain exactly 3 tails. And we have something like heads, 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 tails, tails, tails. Then heads, heads, tails, heads, tails, tails, and so on. So we want to know, just a second. Six, choose 3. Oh, of course. You could look at it this way. You have 3 slots, sorry, 6 slots to choose from. And the heads go into 3 out of the 6. So, for example, heads, heads, head, 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 like this. Therefore, there are 6 choose 3 choices to play for the placement of heads. And once you've placed the heads, there's only one way you can place the tails, right? The tails they're non-distinguishable. We say the tails are non-distinguishable. So if we switch 2 tails around, it doesn't make a difference. So 6 choose 3. That's 6 factorial divided by 3 factorial multiplied by 3 factorial, and that is that should be 20, I believe. So that's 1 times 2 times 3 times 4 times 5 times 6 divided by 1 times 2 times 3 times 1 times 2 times 3. That's 6. 1, 2, 3. Yes, that is 20. There's 20 sequences. Sequences contain exactly 3 heads. Now, the next question is, what is the probability that no 2 heads appear consecutively? That's a different question, and that's a much harder question. So B, no 2 heads appear consecutively. No 2 heads appear consecutively. Well, we need to consider how many heads can we have. We can have so if it's 6, 1, 2, 3, 4, 5, 6. So the maximum number we can have is 1, 2, 3. Yeah, so we can't have 1, 2, 3. There's no way we can do 4, right? Yes. We can't. We can have up to 3 heads. Well, for this question, you would typically get 1 mark for the first question, 2 marks for the second. It depends on the question. We're not very prescriptive. We don't do like mark schemes which are very prescriptive on what do you get marks for. You get marks for correct reasoning, and your tutor is free to decide. And because you will be all marked by the same person. That is, one person marks every single question 1 from all students. So this is the way we know it's a fair system, and everyone gets marked in the same way. So yeah, no 2 heads appear consecutively. So we can have up to 3 heads. We can have 0 heads. We can have 1 head. We can have 2 heads, and we can have 3 heads. Right. So if we have 0 heads, well, that's only one possibility. There's one sequence, which is tails, 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 tails. Easy. 1 head. Well, 1 head is going to be, well, 6 sequences. So heads, tails, 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 heads, etc. Yeah, so 6. I hope you understand why. 6. Now with 2 heads, oh, it's a little bit. It's more complicated, of course, and you if well, let's see how you can do it. You're choosing 2 out of 6, but you can't have 2 tails together. So you could say, let's count how many. Okay. Yes, 2 heads. So we want to avoid situations like this, right? Where 2 heads go together. So there are overall, so how many? So if a head placed here, 2 heads, so 6 choose 2 possibilities. This is sequences with 2 heads. Okay, because we have 6 places, we choose 2. Easy. But if we say, what if the heads are together? Then we treat the 2 heads as 1. And then we have 5 choose 1 sequences with 2 heads together. So overall, we have 6 choose 2 minus 5 choose 1, which is 6 choose 2. That's what? That's the 15. 15 minus 5, which is 10. 10 sequences. 1, 6, 10. Okay. The next one we have 3 heads. And 3 heads, I think it's quite easy. We can just list them. So there's 6, choose 2, minus 5, choose 1. 15 minus 5, because there's 15 sequences with 2 heads. So there's a question, why is it 15 minus 5? Well, imagine you have a sequence of 2 heads and 4 tails. There are 15 possible sequences. But out of the 15, we have to subtract those where the 2 heads are together. And there's 5 of those. Does that make sense? 15, and that's 5. So we subtract 5 from 15 to get 10 sequences. How do you get 15? 6, choose 2. 6, choose 2 is 15. Well, it's 6 factorial divided by 2 factorial times 4 factorial, which would be 5 times 6 divided by 1 times 2, which is 15. Yeah. And 5 choose 1 is 1. 5 choose 1 is 1. Oh, sorry, 5. What am I saying? 5 choose 5. 5 choose 1 is 5. Yeah, so there are 10 sequences where the 2 heads together. Now for 3 heads, I think it's easy enough to just list them. So for 3 heads, it's going to be heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, tails, heads, heads, tails, tails, heads, tails, heads, and tails, heads, tails, heads, tails, heads. Oh, there's only 4. Okay, there are 4 sequences. So that means in total, there are 1 plus 6, 1 plus 6 plus 10 plus 4, which is 21 sequences. And the probability of no 2 heads in a row is 21 out of 64. And that's the answer. Great. The next, a password for a website must, the remaining questions are simpler. I think problem 1 was on the harder side. A password for a website must contain 5 characters, must be 5 characters long and use only letters A, B, C, and D. How many possible passwords are there if characters can be repeated? Well, if you have a 5-character long, 1, 2, 3, 4, 5, you have 4 choices for each character. So it could be A, B, C, or D for each of them. And therefore, there's 4 times 4 times 4 times 4, which is 4 to the power of 5, which is 1024 passwords. Okay. B. How many possible passwords are there if no character is repeated? Well, it goes like this, but now sorry, that doesn't make any sense. Oh yeah, of course. Well, it's sort of a silly question. There's 0. You can't have. It's not possible. But let's imagine there's how many 4-character passwords we can have. And for, okay, let's do 5 character, but we're allowed to choose from 26 letters. Allowed. Put any letter. So the method I like to do is I like to say, well, there are 5 places. There's a 5 letters, and you can choose 26, any out of the 26 letters for the first character. Now you can't use the same character again, so there's 25 characters for the second one, 24 characters, 23, and 22. And then you multiply them and use the multiplication rule, and I explained why last time, because they are not mutually exclusive. And when you multiply them together, you get a value. But there's a short way of writing this value, and that is actually 26p5. This is the short way of writing it. It's similar to choose, but p, and it's actually equal to 5 factorial multiplied by 26 choose 5. It's another useful formula to consider. All right, so that's equal to your calculator can do 26 p5, so it should look like this, 26p5, and it's a big number. 7,893,600 passwords. Okay. Nice. Moving on to question 3. From a group of 10 students, a president, a vice president, and a treasurer must be chosen. How many ways are there to do this? So you have 10 students. It's a very easy question. Students, and you have 3 positions to be filled. And it's the same idea. The first position can be filled by 10 students. The second position can be filled by 9 students. And the third position can be filled by 8 students. So this is choosing where order matters. This is choosing 3 out of 10 where order matters, right? Because you're choosing for different positions, right? If you switch a president with a vice president, you have a different combination of students. Order matters, so that's 10 P3. So that's 10 factorial divided by 3 factorial. 3 factorial divided by 10 minus 3 factorial, which is 8. Well, 1 times 2 times etc. times 7 times 8 times 9 times 10 divided by 1 times 2 times etc. to 7. So everything up to 7 cancels out. We get n times 9 is 772 times 10, 720 ways to choose. Perfect. By the way, I think it's going to be a shorter session today. We'll probably do less than an hour today. How many distinct 7-digit numbers can be formed using the digits 1, 2, 3, 4, 5, 6, 7 exactly once, but the number must begin with an odd digit? Well, let's think of how many there are altogether, with no restrictions. You can write, well, there's 7 factorial, 7 factorial numbers. Why 7 factorial numbers? Well, because you just permutate the 7 digits and you get a different number every time. Or if you use the cell method, you have 7 cells And the first cell can be filled by 7 different digits, second by 6, by 5, by 4, by 3, by 2, by 1, and you multiply them all together to get 7 factorial. So yeah, no restriction, 7 factorial numbers. But if the number must begin with an odd digit, so you start by choosing the first digit. And the first digit can be 1, 3, 5, or 7. 1, 3, 5, or 7. It's 4. There's a 4 possibilities for the first digit. But then the remaining digits, it doesn't matter how you place them. So that's 6 factorial, or 6, 5, 4, 3, 2, 1. So therefore, it's 4 multiplied by 6 factorial numbers. Numbers starting with an odd digit. Okay. Problem 5. In a bag, there are 5 red balls, 4 blue balls, and 3 green balls. 3 balls are drawn at random without replacement. How many different outcomes are possible? Well, here is where it gets confusing. Like the combinatorics, like what do you mean by possible outcomes, right? Because that's the important question. If you say um, picking ball number 1, then picking ball number 1, 2, and 3 is different from picking a ball 1, 2, and 4. Well, it would be true if the balls were not color coded. Like basically, what I'm trying to say, the red balls are indistinguishable from one another. So if you say the balls are numbered and you have 1, 2, 3, 4, 5 red balls, uh, so like 1, 2, 3, 4, 5 red balls, then 4 blue balls, 6, 7, 8, 9, and then 3 green balls, 10, 11, 12. Then you would say there are 12, choose 3 way outcomes if balls were numbered. But they're not numbered, and so they're not numbered, and the red balls, for example, are indistinguishable from one another. So you have to take a different approach. So we don't need that. And let's not confuse ourselves. Right. So as a matter of fact, so it's actually even more simple here. How many different outcomes? Well, the outcomes are that the first ball can be of 3 different colors. The second ball can be of 3 different colors. And the third ball can be of 3 different colors. And that means that there are 27 outcomes. So it's quite straightforward. You can start listing them as red, 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 for example, red, red, blue, red, red, green, red, blue, red, red. Ooh. Aha. I think I've um, hmm. red, blue, blue, red, blue, green, red, green, red, red, green, blue, red, green, green. Okay. Problem with this method is that some of them are identical because the order doesn't matter. Ooh, sorry. Made a mistake here. It's not 27. I think it's just easier to list them. Right, so we have red, green, blue. Red, green, blue. So the possibilities are red, 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 green, red, red, blue, red, green, green. We already have red, green, red. Or red, green, green, red, green, blue, and red, red, blue, blue. Okay, so 6. Right. So now if we start from green, it's green, green. All the possibilities for red, green we already have. So green, 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 blue, green, blue, blue. Aha, yes. And finally we have blue, blue, blue. Oh, so that's nice. So 6, 9, 10. There's 10 10 outcomes. Can't you do question 5 using the permutation or combination formula? You could, um, but because the numbers is quite small, I just prefer to do this. Choose 3 balls. I can't immediately see how you can do it with the formulas, but here I just listed them. Why not? That's a possibility. Okay. And A, B. Now, it says that what is the probability that all 3 balls are of the same color? And it's very tempting to just say, well, there's only 10 outcomes and there's only 3 where they're all the same colors. So the probability must be 3 out of 10. But no, it's not. The reason why it is not, because these outcomes are not equally likely. So red, red, red is not equally likely to, well, green, green, green. Yes, they're not. Yeah, they're not equally likely. But we can go back to the start when we said how many, if the balls were numbered, how many would lead, how many choices do you have? You're choosing 3 out of 12. Choosing 3 out of 12. And it's going to be 12, choose 3. That's the possibilities, which is 12 factorial divided by 3 factorial times 9 factorial. So that's 10 times 11 times 12 divided by 3 factorial. So that's 2. So 120, 220. Possible choices, abilities. Now, out of these, we need to select those which have this same 3 colors. So there's a 5 red balls. So there's 5 choose 3 ways to choose red, red, red. There are 4 choose 3 ways to choose blue, 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 blue. And there are 3 choose 3 ways to choose green, green, green. And so that is 5 choose 3. Is that 10? I think it is 10. So it's 5 factorial divided by 3 factorial times 2 factorial, which is 4 times 2, 10. 4 choose 3, so 4, 3 factorial, 1 factorial, which is 4. And this is just 1. Okay, so there are 15 ways to choose same color. And therefore, the probability of the same color is 15 out of 220. And that is, oh yeah, 3 out of 44. Lovely. Okay, moving on. Question 6. A pizza shop offers 8 toppings. Customers may choose any number of toppings, but no more than one of the same kind. So this is talking about subsets. If you think why we use combinations and not permutations, because the order in which you choose doesn't matter. You have the order of choice doesn't matter. So red ball 1, red ball 2, and red ball 3 are not indistinguishable from one another. So it doesn't matter which order you choose them. The 12, there are 12 balls altogether. You're choosing 3 balls out of 12. Right, so we're talking about subsets. So you have toppings. So let's say we have topping A, topping B, topping C, topping D, topping E, F, G, and H. So there are 8 toppings. So apricots, bananas, chocolate, whatever. A subset, so this is a set of toppings. And like A, B, C, or C, D, or A, or F, G. These are called subsets. Subsets. So the actual question is like, how many subsets there are? So list all possible subsets effectively. So question A, how many subsets of 8 elements of a set containing 8 elements? And the answer is 2 to the power n. It's 2 to the power n, the answer. But how do we arrive to this number? Well, it's we speak about in the assignment. So there are 2 to the power n subsets of a set. So let's look at a simple subset of 3 elements. So A, B, C. And my claim is that there are 8 subsets of this set. So there's the empty set, nothing. So there's A, B, C. So that's 4. Then AB, BC, AC, and ABC. So there are 8 possible subsets. 8, which is 2 to the power 3. So with 8 toppings, that's 2 to the power 8, which is 64 pizzas. Except if you're like me, and I always order pepperoni with pepperoni. So that's but that's not allowed. To have 2 toppings of the same type. And B. How many of these pizzas have at least 1 topping? Well, that's a very easy question. There's only one pizza containing no toppings. 1 pizza containing no topping. Okay, 2 to the power 8 is not 64. 2 to the power 8 is, as a matter of fact, 256. Therefore, there's 255 pizzas with toppings. Yes, thank you. With toppings. Okay. But a subset, by definition, a subset, in a subset, the order does not matter. You can't say, what is a subset? Because a subset like E, F, G, and then is the same as F, E, G. The order, by definition, the order in a subset doesn't matter. But if it did, you just multiply. You multiply the power of the subset by n. So it would be, so 1 subset with 1 plus n plus n plus n choose 2, because you're choosing 2 out of n, times 2 factorial plus n choose 3 times 3 factorial plus n choose n times n factorial. I don't know. This can be simplified, I guess. Give it a go. If order mattered, if order mattered, but it doesn't. But it doesn't. Okay. 6 people are seated randomly around a circular table. Yeah, 6 people are seated randomly around a circular table. What is the probability that 2 particular people, say Alice and Bob, sit next to each other? Well, first of all, it's a circular table. And we want to know how many seating positions there are. 1, 2, 3, 4, 5, 6. The problem is with circular tables that if people sit like this, 1, 2, 3, 4, 5, 6, this is deemed equivalent to people sitting like this, 1, 2, 3, 4, 5, 6. Okay, so this is equivalent. So there's a degree of freedom here. You can rotate the people, and there are 6 possible positions for each sequence of people. There's 6. So you can say it's 6 factorial ways to seat 6 people, but you have to divide by 6 because for each sequence of 6 people, there's 6 positions which are identical. Right? So it doesn't matter where the first person sits. I like to look at it in a different way. I say, okay, there are 6 seats. And for the first person, it really doesn't matter where the first person sits. So we'll just put the first person in the first seat, or in any seat, because it doesn't, how to put it? I had a phrase written down. For seating around a table, as around a circular table, arrangements differing by rotation are considered the same. Okay, so basically, we can just fix the position of the first person. The first person is, I don't know, in a particular seat. There's one choice for the position of the first person. There are 5 choices for the second person, 4 choices for the third, 3, 2, 1. And if you multiply them together, you get 5 factorial. 5 factorial. But also, if you look at this expression, you also get 5 factorial, because 6 factorial divided by 6 is 5 factorial. So either way, you get the same result. But now we have Alice and Bob. For the purpose of this exercise, it's very convenient to consider Alice and Bob as the same as one person. So imagine A and B merge. So now we have 5 seats, and Alice and Bob sit here. There are 4 choices for this seat, 3 choices for this, 2 choices for this, and 1 choice for this. So that's 4 factorial ways to seat. But also, Alice and Bob can sit like this, or Alice and Bob can sit the other way around. So they can sit like this, AB, or they can sit BA. So there are 2 possibilities how they sit, and 4 factorial ways to place remaining 4, and 2 factorial ways to seat Alice and Bob. B. So overall, there is 2 factorial multiplied by 4 factorial, which is something. 4 factorial is 24 times 2, 48 ways. And that's the answer. So that's 48 ways. Lovely. And 2 dice are rolled. Find the probability that the product of 2 numbers shown is divisible by 4. The product of the 2 numbers is divisible by 4. Well, This type of problem can be easily solved by using a table. So this is dice 1 and this is dice 2. Basically, in dice 1 we can have 1, 2, 3, 4, 5, 6. As dice 2 we have 1, 2, 3, 4, 5, 6. So there's 36 outcomes and each of them are equally likely. And we just need to tick those which are divisible, where the product is divisible by 4. So 1 times 1 is 1, so no. 1 times 2 is no. 1 times 3, 1 times 4, yes. 1 times 5, no. 1 times 6, no. So 2, no, no. Oh, yes, sorry. 4, yes, no, yes. So, okay. These are all divisible by 4. These are all divisible by 4. Then 6 times 2 is divisible by 4. 6 times 5 is not. 6 times 6 is divisible by 4. 2 times 6 is divisible by 4. 2 times 5 is not. 3, no, 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 no. 6 times 1, no. 6 times 3, no. 6 times 5, no. Okay, so we just need to select those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's quite a high probability. So probability is 15 over 36. Can you simplify this? Yes, 5 over 9. Sorry, 12. Apology. I don't know I don't know what's happening today. It's 5 over 12, of course. It's less than a half. Great. And oh, so the previous one, what's the probability? So there's 5 factorial ways, so that's 120, and 40 ways, so 48 divided by 120, which is 2/5. So the probability is 2/5. Right, perfect. Oh, okay. How do we get, so I'll go through the question. How do we get all 3 marks? Yes, it depends on the question, so I can't give a description. 15 minus 5, I answered that. 15, answered that. 12, yes. 64, thank you. Thank you for the correction. If 2 to the power n is the order, doesn't matter how much, or if the order mattered, yes, I have expressed that. Will always be 2, yes, it will always be 2. So yes. What is the probability? Oh, I did 40, 2/5. 2, 5. It shouldn't be 48 times 5. No, it wouldn't, because it doesn't matter where Alice and Bob sit, like on because a rotation of the position is counts as the same. Remember, 1, 2, 3, 4, 5, 6 is the same as 6, 1, 2, 3, 4, 5. So no. Were you able to have some physics course? Okay, I literally have maybe 3 minutes to do physics. I'll have a look at question 5 and 6 on physics, and that's all I can do. So let's open physics 5 and 6. Heavy piston is in equilibrium in a vertical cylinder vessel. Well, if the temperature is the same and the mass of this is the same, the only difference is the pressure. The pressure will be different because this piston pushes on the bottom. It squeezes the gas on the bottom. So pressure will be different. Pressure will be different. Different. So the piston pushes, the piston has mass M and cross-sectional area A, so it pushes on the gas and the pressure is force divided by area. So that's what I can say here for question 5. Question 6, a vessel containing ideal gas at 200 Kelvin pressure is connected with a vessel by narrow tube, initially shut by a tap. Vessel B has 4 times the inner volume, so that's 4V and V, and contains the same gas heated until its temperature 500 Kelvin. This is 200 Kelvin. And pressure this. How high will the resultant pressure be of the entire system if we open the tube tap while keeping both vessels at their initial temperatures? Well, you'll need to calculate how much gas there will be. So for the new, you need to use the equation of state. Equation of state. And the equation of state is PV equals N RT. NRT, yes, where N is the number of moles. So we know pressure, we know volume, we know temperature. So we need N1. We need to find N1. We need to find N2. And once you combine the gas, they will have the same pressure. So you can work out the new. So when the tap is closed, calculate N1 and N2 when tap closed, and calculate N1, N2 when tap open. Something like that. Okay, I'll stop here, and I hope that was useful somewhat. And the next webinar is in a month. So once we've marked all your entrance papers and given you all groups, so you can, yes. So I'll see you all in a month. Bye.